So in the previous lecture, we talked about the effects of feedback on applying feedback in an open loop system, how it gets converted into closed loop, and what type of changes are going to occur when you make it open loop system a closed loop one. And we finally summarized the effects of feedback. And now today we'll be talking about Laplace transform. In fact, we are going to talk about the transfer function of systems today. And Laplace transform is a mathematical tool. You might have studied this in previous year. So Laplace transform reminds about the differential equation. Of course, when you talk about solution to differential equation, there is one short hand method called as Laplace transform, and you must have seen the difference between the solution to differential equation, Laplace transform, and solving differential equation. And so, when we talk about Laplace transform, it means that we are going to deal with differential equation. Of course, the control systems are mathematically represented in differential equations form. So this was something that I discussed previously, that whenever you want to solve different control systems, or whenever you want to study, analyze, or interpret any control system or any system, you first have to obtain the mathematical form of it, mathematical representation of it. So we took an example previously where we obtained the schematic of the system. Then from that schematic we obtained the mathematical form, mathematical representation of the system. So likewise, when you try to obtain the mathematical representation of any system, they come in the form of differential equations. And as I told you, that the shorthand method for solving differential equation is Laplace transform. And there was one more method that you studied previously. So for any given input, solving these differential equations give the output response of the system. So which means that if any system is given to you, you want to find the output of that system for an arbitrary input, you will first of all obtain the differential representation of that system, or differential equations that are nothing but the mathematical model of that system. So after obtaining the mathematical representation of the system differential equation forms, you solve it. So there are two methods to solve differential equations. One is solution to differential equation that you studied in second year mathematics, and the second is Laplace transform. So you did both of these. Solution to differential equation was a bit cumbersome, and it was time consuming and very lengthy. It used to give very lengthy solutions. While Laplace transform is an approach that gives you a very short answer, and you come to a conclusion, you come to an answer within few lines. So the basic difference is that contrary to solutions to differential equations, because in solutions to differential equations that you studied, you try to obtain general solutions and particular solutions, and like that you keep on solving the equations. Things were very difficult there. So contrary to this, you have Laplace transform of differential equations that allows to solve complicated dynamic characteristics of the system easily. And of course, to obtain the final response after using Laplace transform is to take inverse Laplace transformation of the final solution. So once you take, because taking Laplace transform is going to change the domain of the system. So you are going to operate the system in time domain. So if you take Laplace transform, that the domain of the system will change to Laplace domain or S domain. So in order to bring back that system to time domain, you will have to take Laplace inverse of that solution to finally obtain solutions. Now, why the Laplace transform makes the differential equation compared to the solution to differential equation? It's easy because it converts the differential equations of the system into linear algebraic equations. So you won't find terms like d by dt's and integrals. So after applying Laplace transform to the system, what you get is the linear algebraic form, and that is very easy to solve. But note that the differential equation describing a control system is in time domain. On the other hand, when it is transformed using Laplace transform into an algebraic form, the equation thus obtained is in S domain. So what is S domain will be discussed later on if time permits, because this is something that we assume you must have been taught to you in mathematics where you studied about Laplace transform. And if you didn't, then because this is not part of syllabus of your course, So if time permits, I'll explain what is S domain and how we deal with. So this is something for the time being you can think of it as a complicated frequency domain. So mathematically, Laplace transform is given by Fs equal to Laplace of Ft, which is equal to integration from 0 to infinity Ft e raised to the power minus St dt. So this is called as one-sided Laplace transform. So in fact, Laplace transform can be obtained both-sided. One-sided means that you're going to take the limit on time from 0 to infinity. For both-sided Laplace transform, the time limit will be minus infinity to plus infinity. So in order to obtain the Laplace transform of any function, you are going to feed ft. For example, suppose that you're given ft equal to let's say t. So you put Laplace of t, or you put t over here. So once you put t here, you get 0 to infinity t e raised to the power minus st, and you're going to solve it. Then what you obtain is 1 upon s plus a. So you can do it yourself. I'll be discussing about the Laplace transform pairs and the table that I will show. So these are the Laplace transform pairs where you are going to find the Laplace transform of ft. So suppose delta t is given to you. So delta t is something called as impulse function. So if you feed this delta t over here, and you solve it from 0 to infinity delta t e raised to the power minus st, what you get is 1. So this is Laplace transform of ft. Likewise, if you feed ut, you get Laplace transform fs as 1 by s. If you solve t, the Laplace transform is 1 upon s square. And likewise, you can see other pairs for which the Laplace transform is given on the right side of the table. So for t raised to the power n is factorial n divided by s raised to the power n plus 1. Then t raised to the power n e raised to the power minus at is factorial n divided by s plus a to the power n plus 1. Then you have Laplace transform of ft, sine omega t as omega over s square plus omega square, cos omega t is s over s square plus omega square, sine hyperbolic omega t is omega over s square minus omega square. So note this, that you have the difference of plus and minus, the sign for sine omega t and sine hyperbolic omega t. Likewise, for cos omega t and cos hyperbolic omega t, there is a difference in the sign plus and minus. So these are some Laplace transform pairs that we will be using in this course to solve certain questions, to find the output of certain models, mathematical or some mechanical or electrical forms. Now we talk about the transfer function. So transfer function, as I told you before in previous slides, that it's the ratio of the output to the input in Laplace domain. So in order to find the transfer function of any system, you first are going to convert that system from time to Laplace domain. So once you convert the system into Laplace domain, then the ratio of the output to the input will be defined as transfer function. So transfer function is a sort of mathematical model. So suppose that you are given a system with input rt and the system gain is gt and the output is ct. So since we are dealing with t, so these are time domain functions, and we say that this is time domain system. And in Laplace domain, you have functions something of this sort. So Rs is nothing but the Laplace transform Rt. Gs is the Laplace transformation of Gt, while Cs is the Laplace transformation of output Ct. So this is the Laplace transformed or Laplace domain system. So for this particular system, the output Cs by Rs is called the transfer function. So up till now, we were not talking about the function S. So we talked about block diagrams, but we avoided S. So the purpose of this was just to make things look easier. So at that time, you might have argued that what is S. So it was not appropriate time to explain what is S. So I simply used terms like R, G, D, C. But these are all function of S. So the transfer function is expressed as the ratio C by R in Laplace domain. And note that the blocks are simple representation of some complex system. So the blocks shown over here, GS, are accompanying some sort of complex system. So for example, this one. So suppose that you're given an electrical circuit and say that the input of V volts was given to this circuit, and you were asked to solve it to find the output V naught. So across this terminal, you were asked to find the output. So one way of solving this equation or this circuit was that you apply the basic laws to it, like Kirchhoff's voltage law and current laws, and obtain all the equations. Then you form the differential equation, apply solution to differential equation, giving you general solution and particular solution. And after that, you obtain output V naught. Let's say for 5 volts. So for 5 volts, you obtain certain output by solution to differential equation. Once again, if somebody say that the input has changed from 5 volt to 10 volt, then what will be the output? Then in that case, you're going to solve this again, applying all the differential equations and obtaining the general solution and particular solution. Then you're going to feed the input in case of 5 as 10. Then you are going to obtain the output. So things will be difficult. You will have to, for different inputs, solve the equations again and again in order to find the output. Likewise, in case of mechanical system, let's say that you apply the force Ft as input to mass m1, and the output was the displacement in mass m2 z. So in order to find the output, you will have to solve the equations associated with it by first of all forming the equations, then applying solution to differential equation. Then for, let's say, 5 Newton, you obtain the output. And let's say the force input changed from 5 to, let's say, 8 Newton. Then in order to obtain the output, you'll have to solve the differential equations again. So this is the place where transfer function makes things simple. So as I told you before, that transfer function is something that remains not to say constant, but fixed. The transfer function of any system is fixed quantity. So it depends upon the parameters that are associated with the system. For example, if you talk about this system, you have resistances, it may have capacitance and inductance as well. So transfer function is something that will be related to the values of these resistance, which are constant. So 3, 3, 4, 1.5, 10. These are all constants, which means that transfer function is something related to parameters of the system and hence will be fixed, always fixed. The transfer function of any system is not going to change. Now, if you once obtain the transfer function of any system, let's say for this electrical system or the mechanical system, so after obtaining the transfer function, what you're going to do is you're going to simply, in order to obtain output for any input, since I told you transfer function is a fixed quantity, for any input you simply are going to multiply the input with the transfer function, since transfer function is output divided by input. So in order to obtain output C, when R is given and the transfer function is given, in that case you will be multiplying transfer function with the input in order to obtain the output, which means that since the transfer function is a fixed quantity, if say 5 volt was given initially, then output would be 5 times transfer function. If input changed by 10 volt, then in that case output would be 10 multiplied by transfer function. So once you obtain the transfer function, after obtaining transfer function, it's very easy to find the output for any input. You don't need to solve the differential equations again and again in order to obtain the output. Likewise in mechanical systems, once you obtain the transfer function of the mechanical system, for obtaining the output, you simply have to multiply any input which is given to the system with the transfer function in order to obtain the output. You may argue that we learned about solution to differential equation and we learned very well how to obtain general solutions and particular solutions, and that was something that we are used to, and we don't know much about transfer function and we don't like it. So, but there are places where you may find it very difficult to apply solutions to differential equation, or sometimes impossible. So here is a case where things may get very complicated. So if you're going to if you're going to obtain differential equations of all the elements within the system, and then you're going to apply solution to differential equation to them, then you might get stuck. I still have shown system which is not very complicated, but there are systems which are extremely complicated, and it gets very difficult to apply solution to differential equations every time when the input changes. So as soon as input changes, the output will be changing, and using solution to differential equation, it is very difficult to find the output for different values of input. So the concept that you're left with to make solutions easy is the transfer function. So once you obtain the transfer function of this particular system or this system, so for any input, you simply have to multiply transfer function of the system with the input in order to obtain the output. So transfer function will be going to make things very easy. And there are certain limitations that I'll discuss about transfer function later on. But for the time being, you can think that this is a sort of mathematical modeling which will make solution to systems very easy. Now, how do you find the transfer function of complicated systems? For instance, if you talk about this system, then to find the transfer function for this system will be again difficult if you're going to obtain all the differential equations related to all the elements. So if suppose that in this particular, if you talk about this particular mechanical system, then you have how many elements? M3, C4, K4. So this is a spring constant, this is damping constant, constant. M3 is the mass of the mass, and K5 is again another spring constant, C5 is another damping constant, and 4 is another mass. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So in this particular case, you're going to have 23 elements, and there will be differential equations corresponding to each mass. So things are very difficult. So in order to obtain transfer function, you will again have to solve the differential equations once. One thing important to note here is that in order to obtain transfer function, you require differential equations to be obtained from the system, similar to the solution to differential equation, where you will be forming the differential equation. But in case of transfer function, once you obtain the differential equations, then there is no need to obtain the differential equations again and again. So another easier method to solve or to obtain transfer function of complicated system is the impulse response. Since the transfer function of any system is equal to its impulse response, that is RT, delta T is the impulse input. We call this as impulse signal. So you studied about impulse input. The impulse signals ideally an ideal impulse looks something like this. So you have a function T, delta T, a function of time. So an ideal impulse is something that will be having infinite values at 0. So we normally show this by something like this. So we say that this magnitude is 1, which shows the area of this impulse to be 1. But in practical situations, you have impulse of this sort. So an ideal impulse is something like this, while in real time you always have impulsive signal of this form. So the duration of this impulse might reduce or increase depending upon what type of application or what type of situation you are dealing with. So ideally we say that RT, which is equal to delta T is this function, and Rs, the Laplace transform value of this function, is 1. So since we know that the transfer function is equal to output divided by input, where if you feed Rs equal to 1, you get C transfer function is equal to Cs. So which means that for system like this, if you are going to apply a impulse input, let's say this is the system. So you provided an input. So you provided an input ft over here, you obtained the output z. So in order to find the transfer function of this system, you simply are going to apply delta t in place of ft. So this will be an impulsive input. So once you obtain the impulsive input, you measure the output. That output is nothing but the transfer function of the system. Likewise in this case, in place of 5 volt, if you are going to apply an impulse input to it, so on applying the impulse input, what you get as output is nothing but the transfer function of the system. So this is what it says, that in order to obtain the transfer function, you will have to obtain the impulse response of the system, and this is something that is applied to complicated systems. For smaller systems, for systems like this, you can simply solve the mathematical differential equations and you can obtain the transfer function of the system. So is it clear to all? Transfer function, as I told you, is also a mathematical model, but before you obtain the transfer function of systems, you will have to obtain the differential equations related to the system. So if you talk about the mechanical or electrical system, there are certain differential equations associated with it. For example, in this particular case, you have two masses attached together with a spring and a dashpot. So there are relations that exist, mathematical relations that exist for spring as well as dashpot and mass. So you will first have to obtain all the differential equations related to these elements. Then you are going to correlate these equations in order to finally obtain the transfer function or mathematical representation of the system. So and likewise in case of electrical networks, you will be providing an input to the system. That may be voltage or current. Likewise, you will be obtaining the output again in the form of voltage or current. And you will be applying KVL and KCL, all laws that you studied, and obtaining the equations related to the circuit. Then you will be finally obtaining the relation between output and input variables only. So all the variables within the system, for example, if you while applying KVL and KCL obtain an equation like in terms of V1. V1 is the voltage at node 1. V2 is the voltage at node 2. So all such variables which have no direct relation with input and output will be eliminated. So when initially solving the equation, you will be obtaining by applying KVL and KCL. You will first obtain the relation between input and V1, voltage V1. Then again you will be obtaining by solving second equation, you will be obtaining a relation between V1 and V2 by applying KVL in this loop. And applying KVL in third loop will give you a relation between V2 and V0. So you obtain by KVL three equations corresponding to each of these loops. Then finally you will be applying KCL, and then your ultimate task is to obtain the relation between input and output by eliminating V1 and V2 and all other variables which are not part of input and output. So once you obtain the relation between input and output for any system, from there you can obtain the transfer function simply by taking the ratio of output to input. So this is something that we'll be discussing in the next lecture, and we'll be talking about how to obtain, or we'll be reviewing, because I think that most of you have studied about obtaining the differential equation related to the basic elements which are mechanical system or in electrical system. So I'll be obtaining the transfer function and doing some examples in the next lecture. And for the present lecture or any lecture that I have taken previously, if anyone has any question, can ask me right now.